So welcome all of you for today's class. We are discussing the physical methods of analysis, and among them we have in this chapter one of the important instrumentation or instruments is Hplc, and we have in the last class tried to discuss some basics of Hplc. So I'll just go through what we have discussed in a few minutes, and then we'll focus on what will be our today's discussion. Okay, so in the last discussion, what we had was the basic discussions on different types of separation technique. We started with that, and we mentioned the extractions and TLC, paper chromatography, and column chromatography. Those things we have just quickly gone through, and then we tried to see the Hplc, its need, and why I mean what types of Hplc you have, different types of Hplc, and then we try to see based on the substrates what type of Hplc can be used, and we also have tried to see the effect of eluents. I mean we have seen two types of Hplc, right? So normal phase and reverse phase, and we try to see which Hplc is suitable for what kind of substrates, and what will be the effect of eluents, right? So that we try to see. Now today what we do is today we'll try to look at the stationary phase of reverse phase Hplc. So what will be the stationary phase, how it is generated, okay, synthesized, that part, and then we'll try to have a comparative discussion on TLC versus normal phase and reverse phase Hplc, and we'll try to look at how the chromatogram will be coming. So impact of polarity of solvents on Hplc peaks, whether it is normal phase Hplc or reverse phase Hplc. If we increase or decrease the polarity of solvent, how it will impact the peak separations or the nature of the peak. And we'll also look at the Hplc peak resolutions and some of the terminologies we use in the Hplc, particularly for I mean the peak resolution related to that. So we'll try to look into that, and at the end we'll if time permits, we'll be looking into the separation with examples, or I mean the we'll try to show you the explanation with different examples and what will be the nature of the chromatogram and how it will be varying with respect to some different parameters. Okay, so this will be our today's discussion. It's more informative, so we'll need to be a bit careful. Now, before going to the details, let us just look at what type of stationary phase we generally use in normal phase Hplc. So among different solid phases, we use the silica is one of the mostly used component. Now, the supports of majority of bonded phase packings for partition chromatography are prepared from rigid silica. Okay, so rigid silica, this is one of the important thing, or silica based composition. So we can have silica related composition. Got it? So these solids are formed as uniform, porous, mechanically sturdy particles, commonly having diameters of 3, 5, or 10 micrometers. Okay. The surface of fully hydrolyzed silica, hydrolyzed by heating with 0.1 molar HCl for a day or two, is made of chemically reactive silanol groups. That is, you have this kind of surface OH will be there. Okay, so the silica, the cage structure, where you'll have a lot of OH functionality, you will have in its surface. Okay, and generally this active OH group is generated by doing hydrolysis process. Okay, with the regular silica we find. And generally it is mentioned you have 0.1 molar HCl is used for 1 or 2 day process. So you take silica, add 0.1 normal HCl and stir it for 1 or 2 days, and then you do filtration, wash with water, and then make it dry. Okay, so this way we can enhance the surface OH, and typically silica surfaces contain about 8 micromole per meter square of OH group. So 1 meter square, that much surface if you consider, you'll have around 8 micromole of OH functionality. Okay, so that is the general way of making active silica for normal phase column chromatography. Now, the most useful bonded phase containing siloxins. Okay, the siloxins are there formed by reaction of hydrolyzed surface with an organochlorosilane. For example, you have this hydrolyzed surface of silica, okay, and you are reacting with a chlorosilane. Okay, so you have methyl, and you have one R group. Okay, so these R, according to our need, we can vary. Okay, now what you do, if you do reactions, this OH can replace the Cl. Okay, and you have the ether linkage. So silicon, you have the ether linkage. Okay, now this modification, what it does is, it has been it is helping to make the surface to be modified with hydrophobic part. Okay, hydrophobic part. And if you take the R as the bigger group, long chain, so your hydrophobicity is going to be enhanced. Okay, so generally the R is alkyl group or a substituted alkyl group. So surface coverage by this silanization process is limited to 4 micromole per meter square or less because of steric effect. So when you are having this bulkier group, definitely it will be difficult to make the all OH functionality to be converted to the corresponding ether group. So you look at here, in general we have the 8 micromole per meter square is the OH, right? And when you do the modification, what we find is that 4 micromole per meter square, or that is being converted. Okay, maximum is we are getting maximum 4 can be reached. Okay, so 4 micromole per meter square. So the unreacted SiOH group unfortunately impact an undesirable polarity to the surface. Okay, but still you have the OH functionality, so definitely you will have the polarity there. So which may lead to trailing, tailing of chromatographic peaks. Okay, so you'll have the impact on the chromatographic peak. Your peak will not be properly resolved. So particularly for basic solutes. So if you have basic compound, you have a tendency to bind easily. Okay, so that's why we need to do further modification. So to lessen this effect, siloxane packings are frequently capped by further reaction with chloromethylsilane. So that means what you are doing, first you are using the bulkier group having bigger R, and then in the second step, what we have to do, we have to just react with trimethyl chlorosilane. Okay, so TMS chloride. Okay, so that we have to use because of its smaller size. So your R is being now methyl. Okay, in later part, so your size is that group is becoming smaller, and then it can nicely bind with other OH. Okay, unreacted silanol. So if I show you the capping property, like capping, how it is done in a schematic way. So here, if you look at, we have the silane where the two, this is a big one, right? And you have here another big one. Okay. Now in between you have the SiOH. If you have SiOH and if you use the basic compound for separation, what it will be doing, you have still the interactions, right? So hydrogen and nitrogen you have, you see, you have still interaction. So due to this polarity, it will still have strong binding. Okay. Now to resolve this one, what we can do is take this one and react with trimethyl silyl chloride, and silyl chloride will be converting this OH to OSI-Me3, and now your problem is solved. So you can use the highly polar compound for the separation. Okay, whatever it is, it may be acidic or basic, so we can use. Now we'll try to look at how the TLC will be comparatively showing, how the peak will be looking at for normal phase or reverse phase if you compare with the TLC. Okay, so say suppose you have the TLC plate here. You have 3 compounds, right? It has been separated, so spots given here. X is being shown. So now it is after elution, what you are seeing, you have 3 components separated, A, B, and C, normal phase TLC plate. Okay. Now tell me here, from this nature, A, B, C, according to polarity, how we can write A, B, C? Can anybody tell? So which one is most polar? Yes, tell.
C is more polar. C is more.
Most polar, right? Then you have B, yes. Then you have A. So A is the most non-polar compound. Okay, so this is we find in the TLC. Now, if you do the separation of this mixture X in normal phase HPLC, what we will see is that the compound A will show peak, compound B also will show peak, compound C also will be showing peak. Okay. Now, since C is more polar, most polar, so C will be coming, the peak will be coming at the last. Okay, so it will take time. Got it? So A, since it is non-polar nature, so A is going to be coming fast. Okay, so if you look at the chromatogram, what we'll see is that we'll find a peak A is coming very fast, then you have peak P will be coming, and then C will be coming. So the chromatogram is with respect to the intensity of the peak versus the time. With the time, we call it as the retention time. Okay, so this is, we call it retention time. Okay. Now the same thing, if we look at to reverse phase column, here I have given C18, where R is having that R group that is having C18 carbon. Okay, 18 number of carbon. Now this reverse phase, what we will see, it will be just the reverse. Your C is coming very fast, which is the most polar, and then B is coming, then A. Okay, so it will be reversive nature. Okay, so it will be reverse. So regular phase or the normal phase TLC is a good indication that you can have the prediction what type of column you can use. Okay, and if you remember, most of the cases we use the separation of polar compounds, right? We generally don't deal with very non-polar compounds. We generally deal with the polar compounds, and your reverse phase column will be more favorable over normal phase column. Okay, because you are interested to separate the most polar compound, so your expectation will be the most polar compound should come early. Okay, and that's why the reverse phase is preferred over the non-reverse or the normal phase. Okay, so let us look at the application little bit. So if I show you here, you have A, B, C, the solute particles where you have the polarities. A is more than B than C in TLC. Now what we do is, in normal phase, you have already learned, so this is the time at 0, okay, and this is increasing. So in normal phase, what we see is that the C is going to be turning fast, then B, then A. Okay. Now, when you have low polarity mobile phase, okay, so your mobile phase having a low polarity, in that case, you will have the better separation. Okay, you have better separation. In medium polarity mobile phase, what is we will be having? We have the peaks are coming very close to each other. So that nature will be looking at for normal phase. This is the normal phase. So normal phase chromatography. This you remember, normal phase chromatography. Low polarity mobile phase will give better separation, but when you increase the polarity of the mobile phase, your separation is going to be decreased. Okay, and you I mean the peaks are going to be coming closer, so your you may miss at some point some compounds. Okay, you may not be able to get proper resolution. Now what we'll be looking at, if you have a reverse phase column. Okay, so in reverse phase column chromatography, high polarity mobile phase, okay, high polarity mobile phase will give you the better resolution. Here in this case, A will be coming first as usual because it is the most polar, then B, then C. So your polarity, if you increase in the mobile phase, your separation is going to be very high. And if you decrease the polarity, if you go for low polarity solvent like medium polarity to low polarity mobile phase, what we will find is your peaks are going to be merged. Your resolution of the peaks will not be good. Okay, so this is the thing you will you have to remember. Now here I will tell one thing. Since you are making the for normal phase, your solid surface is highly polar, right? You have introduced a lot of OH functionality, so it is highly polar solid surface. That's why if you use the compounds which are more polar, okay, what is going to happen? It is going to bind very strongly, but the peaks, the compounds movement will be in a different way, and with the increase of more polarity, the non-polar compound will not move very fast, okay, and the polar compound is going to move faster. So you understand this thing. This is the polar compound A. If we increase the solvent polarity, what is going to happen? A is going to move fast, but B and C, they are relatively non-polar, right? So what is we'll be observing, their movement will be slower. So ultimately, they will be coming closer to each other. Got it? And that's how, with increase of polarity, there is a chance of peak merging or peak separation will be very poor. Got it? Now, if you go for the reverse phase, what we'll be looking at, your high polarity mobile phase will have big separation. So in reverse phase, since A is not binding very nicely with the solid surface, so A movement, which is most polar, movement will be faster. Okay, that we know. And B and C, due to the hydrophobic nature of the solid surface, B and C, they are binding very nicely. Now, if you increase the polarity, what is going to happen? If you increase the polarity, due to the less binding of A, so A is going to be faster, and B and C, with the increase of further polarity of the solvent, the overall hydrophobic nature of B and C is going to be increased. Okay, and because B and C, they are relatively less polar, so if you increase more polarity, what is going to happen? Their interactions will be decreasing. So ultimately, it will bind more strongly with the surface, and your movement will be further reduced. So your separation will be very nice. So A will be coming very fast, B and C will be coming slowly. So your separation will be good. But when you increase the non-polarity of the medium or the mobile phase, what is going to happen? Since A is more polar, it is not binding, so it is going to be moving faster way. Okay, and B and C, you're increasing the non-polarity, okay, of the solvent. So B and C is going to be dissolving in the solvent very fast, and that will also move faster. So ultimately, everything will be coming closer, and you will have a merged peak. Okay, so this is the problem with decreasing the polarity in the of the medium. Now let us go to some terminologies related to chromatogram. Okay, so if you look at here, I have given one chromatogram. We have 3 peaks. This is peak 1. I can write the peak 1. Okay, or the compound 1. This is compound 2. This is compound 3. Right? You have 3 peaks. Sorry, this is you got 3 peaks. Now the compound peaks are 2 and 3, and one is peak which is sometimes we get, okay, in the chromatogram, which is coming very fast. Okay, so the time gap between when you are starting, okay, giving just the click to start the machine for recording the chromatogram, if it is the time, so what we say is that the T0, the time required for a component to migrate through the chromatographic system without interacting with the stationary phase. Okay, so this is the time what you have. Suppose if the component is not interacting the stationary phase, just passing through, okay, how much time it should take. So this is the time gap. Then you have the TR1, the time required for component R1 to migrate through the system. So you have the TR1, okay, so this is the TR1 from here to here. So that is the time gap for the component R1 to migrate, okay, through the column. And TR2, the time required for component R2 to migrate through the system. Now TR prime, TR1 prime is equal to TR1 minus T0. So that means from here to here, if you subtract, so then what we are getting ultimately, this is the thing we are getting, right? This is the part we are getting. So TR1 minus T0, this is the net retention time, or the difference between the total retention time and the dead time T0. So we call T0 also as the dead time. Okay, dead time. So this is
Dead time means
dead time means you have suppose the component which is, if it is not interacting to the column, got it? Then what at what time it will take? Got it? Suppose you have a column, there is no solid surface, I mean any solid phase particle. Okay, you have just the column, the vacant column. Got it? So a column, if you have solid particle, then it will interact in the solid surface, right? The component which is moving, compound is coming here, is going out, right? So this is the length of the particle, I mean the column. Now if the column is not having any solid particle or solid phase component like silica, what it will do? The compound will enter through this point and it will come out through this point, right? So it will take some time, yes or no? Because it has some movement time. So that time we call it the dead time. Now whatever component it is, if you run the column with certain pressure, at the same pressure, two components, they will move almost similar speed, yes or no? Suppose you have a compound,
yes,
because it is not interacting with any kind of solid surface inside the column. So both will move almost similar speed. So they, after passing, they will also peak. Okay, got it? And all peaks will be merging together because all are having the same movement speed. So they will come at the same time. So that's why the T0 is common for all. Okay, suppose your component R1, if it is passing through the column without having any solid surface, it will take whatever time the component R2. So this is, let me write R2. This is, let me write R1. And this is just both of them is coming at T0. So you got it. So that time we call it as the dead time. Okay, the net retention time, when we will be calculating, we have to uh, subtract the dead time with the actual time. Got it? So if you pass this one, the component with the solid surface, then it will take the overall time from here to here is tr1, and we have to subtract the dead time. Okay, so to get the actual retention time of the corresponding component. Okay, so this is the concept of retention time of the component uh, if we use the any kind of column. So this is common for not only, I mean, this is common for HPLC as well as the GC column. Okay, gas chromatography, that. So both things are the same, because both the cases you have some kind of solid surface. Okay, you have a stationary phase there also. Okay, so this is common for both separation. Now let us move to further. So we have a terminology called resolution, which is termed as RS. Okay, this RS of a column provides a quantitative measurement uh, of its ability to separate two analytes. So you have two analytes, and you have when you have two analytes, so I mean two peaks you are expecting, how nicely the two peaks are being separated. Okay, how we call it the resolution ability. So resolution of a column provides a quantitative measure of its ability to separate two analytes. Now resolution by definition is shown here. RS is equal to del Z or Z by half into, so I have to put one third bracket here, WA plus WB. Now what are those? Let us look at. So this is the chromatogram. Okay, you have the dead time here. Okay, Tm is written here, dead time. Now you have two peaks, right? The peak 1 and this is peak 2. So this is peak 2, this is peak 1, and this is the dead peak. Okay, now what I can write is we can consider we can extrapolate here. Okay, along this side we can extrapolate, and if we see it is touching to the baseline. Okay, so then we will get a kind of I mean the triangle, right? Similarly here we can have another triangle. Now this distance, okay, from here to here and from here to here, we call the width of the peak. Okay, so WA, suppose compound A, you have the width here WA, compound B, you have the width here WB. Okay, and what is the del Z? Del Z is the peak point, okay, here for compound A, and peak point of compound B. Okay, if you take that and make the difference, okay, what is the gap size? Okay, so we call it, that is del Z or del Z. Then resolution by definition will be RS is equal to del Z by half of WA and WB. Okay, so that is the definition mathematically expressed. Okay, so now what we can do is we can do the modification. So this is, you have ultimately if you go further, so we can write this way. Now we can replace the del Z or del Z by in terms. Okay, so what we can do is we can replace the del Z or del Z by the overall retention time. So we know that the overall retention time you have from including the date time, okay, including the date time, we can have the overall retention time. So this is your overall retention time for component A. This is the overall retention time, and you have the component B, the overall retention time shown here, right? So that you can replace, so TRB or minus TRA by WA plus WB, so 2 into TRA, this one. You can take the date time also. If you consider date time, then your retention time you have to take it from here to here, okay, from here and then from here to get the del Z value. Got it? So this is we can just look at the retention time and we can replace. Okay. Now the relative retention doesn't provide any information on the quality of a separation, since for equal values of the two very broad peaks may overlap as shown in the trace A. So if you don't have a good resolution, what you can have, if the peaks are like this, so your if you extrapolate the WA and WB, they are sharing some common zone, right? So they are sharing some common zone. So you will have less resolution here, this kind of peak. For this reason, the peak width at half height, so W half, okay, so we have to consider the half height peak, okay, that distance, that width is taken into account when considering the resolution R according to the definition like this, okay. So this half is coming from this problem, because what you have, if you do extrapolate, sometimes we see the peaks are closer, and then getting proper information of WA, then what will be the solution? You just consider the peak height, okay, and then you take the half distance of the peak height, and at that distance, what is the peak width, okay, that you consider, okay, that you consider for understanding the resolution. Got it? So the modified equation is coming like this, and this is we consider further. So in this case, you don't need to consider the 2 here, because you are just taking directly the W half, okay. So the distance, that is the width at half height, okay, width at half height. So that distance you are considering. So this is your resolution equation now. Now here I have given one chromatogram where say suppose the resolution value is coming 0.75. So this is a peak, this is a chromatogram where you have 2 peaks, this peak 1 and peak 2. So a compound A and compound B peak. Now these two, if we consider the resolution, we calculate, say suppose the resolution value is coming 0.75. Now when you are having better resolution, so you see the value is increasing, right? So 0.75 to 1, you see the peak is now coming more prominently, okay. So this was the initial the gap between the baseline to the common zone of the peak, and now that is becoming shorter. So that means you are having better resolution. So resolution value is increasing, and if you further increase the resolution value, if you want to look 1.5, now you have a very nice, the baseline we can see in between the two peaks. Okay, so the better the resolution value, better will be the peak separation. Okay, now we need to know another important terminology. We call it the capacity factor. Now the capacity factor also called retention factor. Okay, we can call also retention factor. It is a measurement or the measure for the position of a sample peak in the chromatogram. Okay, now this is a relative value. You can see here from this particular expression, you have the capacity factor K prime is equal to TR1 minus T0 by T0. Okay, what is R1, what is T0, you came to know already. So you have the overall retention time, you are subtracting the dead time and you are dividing with the dead time. Okay, so this is we are getting as the capacity factor. It's termed as capacity factor. So specific for a given compound and constant under constant condition. So if you don't change the condition, so it will be fixed for one particular compound. Okay, so if you do in your machine, if I do in my machine, it doesn't matter if we apply both cases for the same compound, same condition. Okay, then we'll get the same, like kind of R factor you have seen for the TLC. Okay, we have seen the retention, I mean the R factor, right? You have distance traveled by the compound by the distance traveled by the solvent. Okay, but if you do at different places with same percentage of solvent ratios, we'll get the same R factor, right? It's kind of like that. So specific for a given compound and constant under it is constant under the constant condition. The function of column and mobile phase chemistry, definitely it is a mobile phase chemistry, and it's related to the how much polarity of the solvent you are using and all, and definitely the column you have the solid surface, so it is interacting with the surface. So definitely both the having a role here. So that's why your condition you need to be fixed to get the same capacity factor. Okay, so we call in the TLC the R factor, here we call it the capacity factor. Now preliminary or the primary applicable under isocratic condition. In general, a change in the K of one peak will move all the peak in the same direction. This is important. So if the overall chromatogram, if you look at, so you will have the individual K for each component. Now, if you change the condition, if the K is moving from its primary distance, I mean primary position to a certain position, if you change the condition, the similar movement will be looking at for K of another compound. Okay, in the same direction. If the K is moving to the right, okay, so we'll see the other compound will also move, the K of the other compound will also move to the right. So we have another terminology, the selectivity factor, so also called separation or selectivity coefficient, which is defined as alpha, indicated as alpha, and alpha is you have the K2 prime by K1 prime. So that means you have two components and their relative position. So the K2 by K1, okay, which is coming later, we consider that is as the K2, so R2. So with respect to that K2 by K1, it's not the K1 by K2, it is K2 by K1, which is expressed as alpha, which is termed as selectivity factor. Okay, so that is also there. So function of column and mobile phase chemistry definitely is related to mobile phase and solid phase or the stationary phase. And similar condition you have to consider. So isocratic condition, it is applicable if you are don't having similar type of condition. We don't apply this one because for a compound with different conditions, we cannot just compare them. Changes in selectivity will affect different compounds in different ways. Definitely you have, if you apply the different conditions, your selectivity factor will be changing. Now let us quickly see. Okay, I think you have another class, so I'll just finish this slide and we'll stop here, and then we'll move from here further in the next class. So quickly, if you look at, you have this figure, okay, and this figure you have the different values are given. you have K1 prime is 2, the K2 prime is 3, and here the alpha is coming 3 by 2, it is 1.5, it will be, it is 1.33 written, K2 by K1, so K2 by K1 will be 1.5, so this is 1.5, and then you have N2 is equal to 114. Okay, so this is the situation. Now this side the K is decreasing side, this side K is increasing side. So that means this is the K, this is the for 3, and this is for 2. Okay. And then you have another chromatogram you look at. Now what I am trying to tell here, you have K1 and K2. Now if you look at the difference between K1 and K2, here K1, K2, 2 and 3, the value 2 and 3, here value 1 and 1.5. So value is decreasing, right? From here to here, if you move, your K1 and K2 value is decreasing, and if you see the peak resolutions, that is also decreasing. Similarly, if you go here to here, so 3.7, 5.25, your K1 and K2 value are much differ from each other, so your peak resolution is increasing. Okay, so in another way we can tell, you have the capacity factor, and this capacity factor can be indirectly indicating the resolution. Okay, so this is the thing. And when you have much differ 1.5, okay, this is the alpha is given 1.5. When the value is too much varying, I think you can give it more, give the more value. Okay, so if your value of alpha K2 by K1 is even more, you have further resolution. That means you have the K1, K2 is differing much more. Okay, so ultimately the selectivity factor or the capacity factor, they are indirectly telling you the resolution information. Okay, so I'm stopping here. We'll meet in the next class. If you have any queries, just go through, I'll be giving, and if you have any queries, let me know. Okay, so thank you for attending today's class.
Thank you, sir.
Thank you, sir.
Thank you.